In the previous lecture, we were discussing about the thin film equations. We will continue with that. So, the physical situation that we were considering, although this physical situation is just an example, it should not be considered as a general scenario, that you have an inclined plane with an angle of inclination theta and there is a thin liquid film. On the top of it, this film thickness is in general not a constant, it is a variable. So, this is h, which is a function of x and time. So, this is the dimensional x direction, this is the dimensional y direction. We have arrived at the following equations for 2 dimensional and incompressible flow. What are the governing equations? After considering that the characteristic H naught is much less than LC, so that epsilon which is H naught by LC is much less than 1. With this consideration and solely this consideration, and of course with a consideration that the product of epsilon square and Reynolds number is not large. So, Reynolds number is not abnormally large, that even if epsilon is small, Reynolds number into epsilon square is moderate. So, that situation we are ruling out. Our hope is that even if the Reynolds number is moderately large, epsilon is so small that epsilon square is very limitingly small and epsilon square multiplied by Reynolds number will be negligible. That is our intuitive hope. So, with that the continuity equation will be, continuity will be always important. These are the momentum equations. So, this mu del to V, this term itself is not there. So, we have so, you can see a very interesting thing along the y direction, which is across the film thickness, the pressure variation is like a hydrostatic pressure variation, purely gravity driven pressure variation. Okay. So, now these equations are fine, we have given detailed considerations how different terms are dropped, so that these simplified equations are arrived at. I am not going to repeat that in this lecture anymore. Now, we should concentrate more on what we require so that we can solve these equations. So, out of these equations we really do not know U, V, P, these three things we do not know. We also do not know another thing which is hidden in this equation, because everything is expressed in terms of film thickness, but film thickness is not given to us a priori. So, H is also not known. So, H in a dimensional H, say H prime. So, this film thickness is also not known. The thin film problem that we discussed as a special problem in the context of exact solution of Navier-Stokes equation, the difference between that and the generalized thin film theory that we are doing is that there this was taken as a constant. So, this was no more a variable for the problem, but now this is a variable for the problem. So, you require enough boundary conditions to solve this problem. So, what are the boundary conditions that you must consider? So, first of all we will consider a boundary condition or the boundary conditions at the interface. So, to highlight that this is not flat, let us draw it like this, so that you never keep that prejudice in mind that it is flat. Under certain condition it may be treatable as flat, but in general not. So, what are the boundary conditions at the interface? That is the first question that we would like to answer. The boundary conditions at the interface are typically as follows. So, one type of boundary condition refers to force balance at the interface, and therefore, they are kinetic in nature, they refer to force balance. And another boundary condition at the interface purely follows from kinematic constraints, and that is called as kinematic boundary condition. So, we will start with the force balance boundary conditions and then we will arrive at the kinematic boundary condition. So, I am erasing these equations, we will come back to these equations once more when we non-dimensionalize the governing equations and so on. So, when you have an interface like this, the two important directions for the interface are in terms of the curvilinear coordinates s and n directions. These s and n directions are very important. So, force balance, we will write one force balance along s direction, another force balance along n direction. So, along the s direction whatever force balance we write, we call it tangential force balance. So, how to write a tangential force balance boundary condition? To understand it clearly, what we will do is we will consider a flat interface first. Example 1, flat interface, and then we will extend it to curved interface. So, for a flat interface, let us say this is an interface. So, this is like a edge view of the interface. In reality, it is something like this, you know, as a flat membrane, so to say. So, now let us say that we have a force balance at the interface. So, on this side there is gas, or I mean a phase which is having much less viscosity and density as compared to what is there on the bottom side, that is what is our assumption. So, if that be the case, we are not really bothered about what is there on the top side, and the bottom side there is some liquid. So, now at the interface there can be a variation of temperature along the tangential direction. If there is a variation of temperature or composition along the tangential direction, there will be a variation in the surface tension force, because surface tension is a strong function of temperature and composition. So, if there is a variation of the surface tension force, if the surface tension here is sigma, and here, so if this length is dx, this is sigma plus d sigma, right. Let us say this length is 1, the width is 1, this dimension is 1. So, sigma into 1, this is sigma plus d sigma into 1, right. The other force which is acting on the free surface is the shear stress, tau. So, the tau, if it is like this is tau into 1 into dx, right. Remember, surface tension is force per unit length, so that is multiplied by length. Shear stress is force per unit area, so that is multiplied by area. Okay. So, this is the free body diagram of this, you know, elemental membrane at the surface. I mean, this is a fluid membrane, this is not a solid membrane. So, for equilibrium, you have resultant force along the axial direction equal to 0. So, minus sigma plus d sigma minus tau dx is equal to 0. So, tau becomes d sigma dx. Okay. So, this is for a flat interface. Now, the sanctity of the x direction gets completely lost if the interface is undulated. Then what is, I mean, then what matters is the local tangential and the local normal direction. So, to appeal to that, instead of writing the tau along x, we should have a resolved component of tau along s. So, how do you resolve the tau? Remember the relationship between the traction vector and the stress tensor. So, let us write that first, because this tau is nothing but, a component of the stresses coming from the stress tensor along the x direction. So, first of all, what is the traction vector? Let me write it in index form so that right. This is what is this I is equal to 1 means x, I equal to 2 means y, I equal to 3 means z. It is a 2 dimensional problem. So, only I equal to 1 along x and I equal to 2 along y. So, you can get the components of T. If you get the components of T, you can constitute this vector, for which I equal to 1 will be the x component, I equal to 2 will be the y component. So, the resultant will be this vector. So, now this vector will have a component along the s direction. Right. So, this vector will have a component along the s direction, that is this one if the surface is undulated. So, left hand side little bit more straightforward than the right hand side. Right hand side, instead of finding the derivative of sigma along x, you need to find out how sigma varies along the s direction. So, for that we will use, first of all, this is the component. So, we will write it in a vector form by multiplying this with unit vector along s. Okay. So, this is the vector form of this one, that is the component along s, this is the component along s, this is the total traction dot product with s, s is unit vector along the s direction. So, this with multiplied with the unit vector along s will give the vector form of the stress. This is equal to, instead of this simple one dimensional thing, okay. So, because they are all in the same direction, so we will just eliminate the directional part of it, because this is a resolved component already, this is already a resolved component. So, this also has to be a resolved component, right. Okay. So, why I have dropped the s here is because it is unnecessary to write it in a vector form. This we can write it in a scalar form, and the scalar form is a resolved component of the vector along s. So, we are similarly writing the resolved component of this vector, instead of variation along x, it is variation along s, and I will explain what is this surface. This is called as surface gradient operator. So, just from a vector calculus angle, when you write different terms, make sure that the terms in the left hand side and right hand side are consistent. So, see, this is a vector, this is a vector, dot product of the vectors is a scalar. This is a sort of a gradient operator, not really the traditional gradient operator, but surface gradient operator, but a gradient operator operating on a scalar will make it a vector. So, this is a vector, dot product with a vector will also make it a scalar. Okay. So, now the question is, what is the surface gradient operator? So, to understand that, we will take an example of acceleration vector. So, acceleration as a vector is a vector sum of the s component of acceleration and n component of acceleration. So, as is a minus a n. So, what is n? N will have a unit vector in the direction of n. So, this is the vector marker for n and its scalar component is nothing but this one, right. So, in this way you can write grad s right. This is just, do not take it as a derivation, right. It is not that I am deriving this operator like this, but it is an analogy, that the analogy is that it is like the component of grad along S, just like component of any vector along S. So, the philosophically it is similar, but of course, this is just an algebraic quantity and this is a vector operator. So, the they are not exactly the same. So, we have defined grad S sigma through this expression, and this in a way defines the tangential force balance. So, now what we will do is, we will generalize this a little bit, in a sense that not generalize, but we will write it for a dimensional form first. So, because we were talking about the dimensional variables x and y, so we will write dash at the top of all the terms, just to be consistent with our symbol in this particular chapter. Dash means all dimensional quantities. So, these are dash dash. N and S we should not put dash, because N and S and N dash and S dash are all the same for. So, N is fine. So, S and N we can write without dash, but others we should write with dash, right. I think I have done that. So, we have mentioned the tangential force balance. Then we will consider a normal force balance. Imagine that the interface is in static equilibrium, where on this side pressure is P naught and on this side pressure is P. So, you can write the pressure P at the surface, which we call as Ps minus P naught is equal to sigma by r, where r is the radius of curvature of the interface. It is a planar problem, so R1, R2 all those things do not come. So, this is the basically the Laplace pressure that we are talking about. This is the surface tension locally and this is the radius of curvature of the interface locally. So, we should give dash also to all these terms. Question is that is this same equation valid under dynamic conditions? The answer is no, in general not. Why? Under dynamic conditions there is also a viscous normal stress in addition to pressure. So, this is we should clearly write under static condition. Under dynamic conditions you have to augment this with viscous normal stress. So, how do you find out the viscous normal stress? So, the traction vector dot with n, the tangential was component was dot with s, this is dot with n. And why we are putting a minus sign here? Because pressure by definition is compressive, whereas this by definition its positivity is tensile. Now, this is not all. Why this is not all? Because of a very interesting physical phenomenon. When the film thickness becomes smaller and smaller and smaller, there is a critical film thickness when the van der Waals forces start becoming important. So, when the van der Waals forces start becoming important, the equivalent van der Waals forces which you represent in a pseudo continuum type of framework is represented by a augmented pressure called as disjoining pressure. So, or excess pressure. So, we will consider that is there even under static condition. So, we will have an additional term which we call as the excess pressure or disjoining pressure. And typically this is not a constant because it is a function of the local film thickness. So, this will roughly scale with, say for example, it depends on what is the kind of a situation, but typically it will scale with 1 by h cube typically. So, if the film thickness is smaller and smaller and smaller, this will become so much so that it may overweigh all other terms in this equation. So, to summarize, in this lecture we have discussed the force balance boundary conditions at the interface, normal force balance and tangential force balance. What we have not touched upon till now is what would be the kinematic condition at the interface, and that we will take up in the next lecture. Thank you very much.